Okay, so today it's our pleasure to have Matti Järvisalo here, who will tell us about implicit hitting set approaches and remove Zoom messages. And for the second half, we will also have Jeremias, who is not on camera. So without further ado, Matti, we're happy to have you. Please take it away.
Thanks very much. Happy to be here. Thanks for attending to celebrate the Independence Day of Finland. It would be a day off, but we'd rather be here in Copenhagen. Wow. Of course. Yeah, so this will be, so my part will be on a very sort of a high level introduction to what is the so-called implicit hitting set approach to solving hard optimization problems. And I'll try to sort of convey the idea that you can implement it for various types of hard optimization problems. Hopefully I won't bore you. Hopefully there's something new for everyone to pick up. Feel free to ask questions. Before I start, let me thank that I ripped off many of the illustrations from Paul Saiko's actually Lectio Precursaria, which is a presentation he gave at his PhD defense. Because his PhD that I supervised was actually on developing some of these IHS approaches that I'm talking about today. So the agenda for today is that, as I said, so the first part will be by yours truly. So I'll give a sort of a gentle introduction to what is implicit hitting set approach. And then Jeremias here will then take over for the second part and talk about a specific instantiation of IHS, the pseudo-Boolean optimization, with hopefully a bit more details on actually how things are done when instantiating the approach. So what are we dealing with here? So our focus is on really developing practical algorithms, what we like to call solvers for problems that are very hard to solve. Won't be hard optimization problems. So we're dealing with something like this. So we have an objective that's a linear function over some discrete variables, and then our solution space from which we want to find an optimal solution out of is characterized by a set of constraints. And what the constraints are depends on how we choose to represent the constraint. And really, so we want to, so our particular focus tends to be where you talk about the implicit hitting set approach are problems where it's actually even hard to decide whether there's a solution to the constraints itself. And we also want to sort of devise or develop exact optimization procedures, so meaning that solvers that can provide us probably optimal solutions given enough resources. And the third sort of but is that we are actually interested in developing generic solvers that are efficient for real-world instances of hard optimization problems, not potentially to claim that we can solve all problems that are hard for NP, really fast. Okay, so what is the implicit hitting set approach? So it's essentially, in its generality, it's a generic framework for developing practical algorithms for hard optimization problems. And sort of the I left in a citation here. I was supposed to actually remove all citations from this slide because there would be too many and I would anyway miss some. But let me just mention that so this sort of the generic framework builds on really early work from the 80s by Reiter and Reggie. Typically Reiter is cited here, but there's another group of folks who were proposing something similar already in the 80s, I believe. And then these ideas were picked up. So this is where the so-called hitting set duality notion comes from, I believe. So then in early 2010, so these ideas were picked up again, so reintroduced, I believe, to some extent, by Karp and others who actually talked more about a generic framework where that is the hitting set approach, but however they were really restricting to to problems where it's polynomially it's sort of it's easy to test the feasibility of hitting sets, and hopefully this becomes clear what I mean by this. And at around the same time, so this was picked up in the realm of constraint optimization, maximum satisfiability by Fahim Pakus and Jessica Davis, who developed a solver for MaxSAT based on the implicit heating set approach, which still sort of is one of the most practically efficient solving engines for MaxSAT today. And building on these ideas, then there's been a huge pile of developments to developing IHS approaches to further constraint languages, satisfiability modular theories, pseudo-Boolean optimization, as Jeremias will tell us about more. To answer set programming, this is what we've done as well, and to finite-domain constraint optimization problems and so forth. As well as sort of something that could be considered more sort of application-oriented work. Well, it's sort of, it depends on who you ask. Is it application work? But there's been various works developing implicit heating set approach to inconsistency analysis in different constraint languages. So finding, for example, smallest explanations in terms of unsatisfiable sources of unsatisfiability. To unquantified and quantified representations, as well as domain-specific approaches. I'll mention something about these today, hopefully, if I won't run out of time. And we sort of also have a paper, by the way, with Paul from his thesis that sort of expands on how this framework is really generic, and you can actually go beyond NP and to solve even harder optimization problems than say MaxSAT with IHS. This is very much a hybrid approach where we're actually not just developing directly an optimization solver for specific language, but we're developing a solver that sort of makes use of both decision solvers and optimization solvers in an iterative fashion to then achieve the goal of solving the optimization problems at hand. Okay, so now comes the time to sleep a bit for those who know what implicit heating sets are. So I'll start with heating sets. So hopefully everyone knows this, but if not, let me remind you. So we're dealing with the universe of elements, a finite set of elements. There are these black dots or circles. And then we're given a subset, a collection of subsets over this set of elements that are illustrated with these rounded rectangles here. And it turns out we're going to be calling these things cores for a reason that hopefully will become obvious later. And now a heating set is just what our task is to select a subset of these elements such that we pick an element from each of the given sets in the collection of subsets of these elements. So here's one heating sets of these sets over these elements, because so we have 5 subsets, but we can hit them all by selecting 3 of these elements, the yellow ones. And now finding a minimum cost heating set or a smallest heating set, if we just consider these elements as such, is NP hard. So it's an NP hard optimization problem in itself. And we could then introduce even a sort of cost on selecting individual elements to hit the sets with, and then we'll be talking about minimum cost heating set problems. And this is what we're of course going to be talking about in the following as well. Okay. So how do we get from heating sets to optimization? I'll try to convey this example, actually prepared by Paul originally, but it's a neat example, I think. So let's consider the problem of Maxcut. So where we're given a graph like so, and our task is to find a partitioning of these nodes in the graph, given a graph into 2 sets, such that we're maximizing the number of edges between these sets. Okay. So here's one partitioning. So one partitioning are the nodes represented in pink, and the other partitioning consists of the nodes colored in blue. And the number of edges that we're cutting is 4 here, the green edges, right? So what are we doing really in Maxcut? So we're maximizing the number of the edges that we are cutting. So, but we're looking for a partitioning that maximizes the number of edges between the nodes in the partition. So in one way, we can think about the underlying constraints being that for each edge, we would prefer that the endpoints of the edge would be in different partitions, right? And let's denote this by this. But now why can't we just sort of partition into 2? Well, because the graph sort of has these constraints give us sort of notions of conflict or so-called force. And these here essentially something that incur cost that arise from sort of odd cycles in the graph. So if you look at this triangle, for example, because we are partitioning into 2 partitions, we know that there's no way that we can sort of get 3 edges from this triangle that we can cut by partitioning into 2, right? Because it's a clique of size 3. It's a triangle. There's 2 more odd cycles of length 3 here, like so. And each of them essentially give us this sort of a constraint saying that, well, it has to be the case that either you can partition these 2 guys into the same partition, into different partitions, or it has to be the case that you can partition these guys into different partitions, or it has to be the case that these guys can be in a different partitions. So to put it otherwise, either these guys has to be in the same partition, or these guys, or these, right?
Right, is this bar on top a negation, or what?
Yeah, it's sort of intuitively, right? So this if we talk about not being in the same partition, then this is saying that no, have to put into the same partition or have to put into the same partition. Yeah, right? Sorry about that. So these 3 cycles of length 3 give you this, and there's the 4th odd cycle, which is this here. So it gives rise to this, and we're going to call these cores. And these are the reasons why we can't actually partition everything so that we could cut each edge, right? And it turns out that now nicely, if we compute a hitting set, so consider these are elements, sets that we need to hit in a hitting set problem over these guys here, these elements. Now, if we find a hitting set for these cores, then this maps sort of an optimal hitting set, so a minimum hitting set over these cores. Then this maps into an optimal solution to the Maxcut instance. So see, for example, here we're hitting by selecting this. So we're hitting these cores, and another thing that we're hitting with is this. So we're hitting these cores. So what this means is that this gives us a partitioning that, so this hitting set forces these guys, which are these edges that we sort of the hitting set tells us that we can't cut. These set tell us A, C, and D belong to the same partition, and the rest can go to the other partition. And this is actually one of the optimal solutions to the Maxcut instance. So we're essentially finding optimal solutions to an optimization problem by finding an optimal hitting set over the set of cores underlying the problem. And the definition of a core depends on the problem. But the elements pretty much are sort of weighted soft constraints, or you can also more abstractly view them as sort of objective function terms. And a core is then a subset of soft constraints, one of which must incur cost. So it means that we need, for each core tells us that, well, you need to actually incur cost by sort of hitting one of these terms. And then a minimum cost hitting set of all cores, if we would have all the cores, then this would immediately give us an optimal way of sort of incurring cost, which means that we would have an optimal solution to the optimization problem. So then we're done, right? So, okay, so the issue is that, well, we could so simply compute all cores and just find a minimum cost hitting set, and then we're done. Well, there's perceivable problems because, of course, most generally there's an exponential number of cores, just like in the Maxcut example, for example. And this would then, of course, so first of all, if we would want to compute them all, this would take a lot of time, and actually it can be hard to compute even one core most often. And then we would have a huge hitting set problem over this exponential size set of cores, and which is then behind to solve. Optimal. Okay, so that's problems.
Obvious that I'm just thinking that the fact that if you satisfy if you have a minimal hitting set of the core constraints, that you in fact get an optimal solution. That is because you have some. Wait, so how does this go? You have some objective function. I can think of it as you want to minimize things, and a core I should think of as a constraint telling it will sort of be out of these objective variables I have to give up on at least one.
And if you have
if I have all these constraints and I'm satisfying all of them in the cheapest possible way, then if I just think carefully about it, I realize that now this has to be an optimal solution because I have to satisfy all of these core constraints.
You're essentially relaxing
so
away.
No better.
Yeah,
solution.
You're optimally removing these sort of costs that you have to pay for.
And if this was not a solution, that just means that then I've missed to list some core that is not yet there.
Exactly.
So that's why sort of
there's another core that restricts you of having a solution.
Okay. So just by definition, a minimum hitting set of the core will be an optimal solution to the problem.
Of all cores.
Of
all cores. Yes. Sorry. Yes. Thanks.
And now, so because we don't hopefully want to compute all the cores, so then what generally, or the generic implicit hitting set approach is an iterative approach where we essentially accumulate cores iteratively, and then after accumulating one or more cores then we always compute the hitting set problem over the current set of cores, and then we go about checking whether we've already sort of hit all cores by checking if the rest of the problem admits now a solution for it. But this is in hope of finding a minimum cost hitting set of all cores before actually computing all cores. So yeah, these are the pictures that we always like to draw. I guess I'm the fault here. So I always like to think about IHS as this type of a figure. So essentially, whatever optimization problem is, we get some input instance. It has an objective function and it has a set of constraints that we're optimizing with respect to subject under and yeah, and so we're sort of separating the objective function and the constraints. So the constraints give rise to cores, and the objective function then is dealt with in the hitting set computation. And now really the idea is that we have an algorithm box that computes us a core. If there are cores that haven't been hit by a hitting set problem, hitting set that we have, the latest hitting set that our hitting set optimizer has given us. This is sort of added to the accumulated hitting set problem, and then it's solved again, and it provides always us a new hitting set. And the hitting set, essentially the cost of the optimal hitting set for this subset of cores that we have accumulated always gives a lower bound for the optimal cost of the actual optimization problems that we're dealing with, because of course it might be that the hitting set doesn't still implicitly hit all the cores because we don't know all the cores. So the hitting set that's given by the hitting set optimizer then gives us a way of saying that, okay, these work, so extract the core, but bear in mind that, look, these sort of soft constraints are now relaxed away, which are in this hitting set, well, with which we actually sort of hit the current set of cores that we have. And this cycling goes on until the core extractor says that, look, the hitting set that I just got actually turned this instance that I'm working into an instance that admits a solution. And then that solution will be then guaranteed to be optimal because assuming that the optimizer gave us a minimum cost hitting set, because it implicitly hits all the cores. So really naively thinking, so I mentioned this hitting set problem instance. So if you think about it, so what we are actually, the algorithm is doing is starting with an empty set of subsets to hit. So empty set of cores, we can hit it by anything. So we don't need to hit it by anything. So, but then we extract the core. There's a core, and then it's unhit currently by our empty hitting set. So we need to hit it somehow. And then we're going to ask if there's another core. Yes, subject to the fact that we're hitting with this element, relaxing this element away. Well, there is another core that's not hit. So now if you compute an optimal way of hitting these two sets, it's going to be this element. So the hitting set just sort of flips into that guy. And we're going to ask again. We get this iteratively accumulating these cores. Now we actually need to hit with two elements because these three cores are not sort of, they don't have they have an empty intersection. And so forth. And the neat thing is that for this example, for example, so in this after receiving these three cores, we already managed to hit the remaining core that would come afterwards. So this wouldn't be extracted, but we would terminate before that. Okay. So with the fear of repetition, though, let me still mention what are cores still and a bit about how to compute cores. We haven't talked about it yet. And then how in practice do we compute optimal hitting sets given a set of cores? So how do we solve the hitting set problems? And then I'll mention a bit about not quite a bit, quite a lot, but a bit about how to make it actually perform well in practice. But that's the last thing. And before actually that, I'll try to use some. If I have enough time, I'll go through a couple of instantiations on a high level of this paradigm.
So we should think of this core extractor thing as you're going to feed it a candidate solution. And you're either going to get back, yes, this is a solution to all the constraints, or like
subject to the hitting set that relaxes away the cores.
Or we get back like, no, here's a constraint that you maybe were not aware of, but like this doesn't, you have to also satisfy, or you have to pick one of the following. Like here's a set that you're not hitting.
Yes.
And
here's a reason that says that at least this hitting set does not result in an optimal solution. So it could be that you might have to incur more cost to hit all cores.
Which it's somehow some kind of online version of hitting set where you're trying to hit, but the sets are revealed to you one at a time.
Yes.
but only when you fail to hit the set. Every time you fail to hit the set, then the oracle says back to you, well, actually, I had one more set. Here it is, and you're not hitting it.
Yes.
But then you
And
know that.
Yeah, it's a very odd version of the
Some kind of adversarial online version.
Yes. Yeah, so just to reiterate, so the cores are what are cores? So essentially you can think about if we think about so one view to optimization problems is to think about constraints and objective functions expressed as weighted soft constraints. So each term in an objective function is essentially a unit a soft constraint that has a weight that's its coefficient. But you can just think about a list of constraints. Some are hard and some are soft. Hard you need to always satisfy to have a solution, and the weighted soft constraint give you the cost function. This is sort of the viewpoint that finite domain constraint optimization people sometimes take, and also in MaxSAT this is the view that's typically taken. So the cores are subsets of the set of soft constraints in our input instance. Essentially, what type of constraints are they? So if you recall the MaxSAT instance, so we have these sort of logical ORs that are the cores, but they are pretty much sort of an OR is just an at least one constraint, saying that you need to hit at least one of these to incur the necessary cost. However, so in more generally, and especially so relating to what Jeremias will present on pseudo-Boolean optimization by IHS. So generally, cores are simply just constraints of the objective function variables in our instance that are entailed by the constraints of the problem, meaning that any solution to the constraints subject to which we're doing the optimization also has to satisfy the cores. And this is a very general notion of a core, right? So it's not really, so if you think about this definition, you're allowing any type of a constraint that's just sort of satisfied by any feasible solution to the constraints that we have. So they're not at least one, we're not restricting to at least one constraints anymore then. And hitting set problems arise from these at least one constraints, right? So if we sort of scratch this view and take a more general view, then it's not really a hitting set problem anymore that we're dealing with, right? But we can still, of course, solve it with an optimizer. Yeah, so that's the point. So in general, there's no need to restrict if you're hitting set constraints. Does it pay off to do something more general? That's up for grabs to some extent. So how do we do the core extraction in practice? We didn't talk about it really yet. Maybe many of you really know, but we're essentially most commonly when instantiating the hitting set approach, implicit hitting set approach, we're relying on the declarative approach. So we're essentially building on this idea that whatever optimization problem that we're solving, we're going to express it in a declarative language, in a mathematical constraint language, and then we're essentially going to choose a constraint language for which there's practical decision solvers for that actually can have these core extraction capabilities available. And when we actually take the declarative view, then the notion of cores becomes sort of evident because it's just defined for the constraint satisfaction language. So we don't need to always go and think about what is a core in this optimization problem. Rather, it's handled by our core extractor. That's sort of nowadays an off-the-shelf solver, especially when it comes to, for example, Boolean satisfiability solvers or their extensions, which essentially can give us these cores without overhead. So when they would go about deciding satisfiability of propositional formulas, they realize that they provide an unsatisfiability proof, they can immediately give us also a core that explains it. Now for the other parts of the optimization part, so the standard approach almost always this is not said that you always would have to use an integer programming software, but most often is that of integer programming. So you just simply sort of phrase the heading set problem as a very standard way, in a very standard way as an integer program. So what this is saying that we have a accumulated set of cores, then we go through all the cores, and for each core we're going to state that for some variables we have a sort of an indicator variable for each element in the cores, and then we're going to say that, well, you need to assign at least one variable to true to one for each core, and then the cost function of our problem is here, so we're just accumulating cost by heaping. One thing about the notion of cores, so as I said, so if you don't need to restrict to at least one constraint here, you can essentially express any constraints here that you can express with as linear inequalities, just like Jeremias will talk about, but you're free to sort of add constraints to this problem. Then it's not really a pure heading set problem, but who cares? Okay. How much time should I use?
You have like until the hour.
Okay. All right. Okay, so let me switch over to
earlier.
We can switch over to let's switch over now to sort of I'll try to convey some ideas on how this sort of general paradigm is then instantiated for different kinds of applications. And what I have on the slides is one example for really sort of declarative optimization on MaxSAT. This is probably for this audience the most well-known thing regarding these three that I chose, and then I have an example of how to do something called propositional abduction, and this is actually a problem that's harder than NP, so we're going to the hard for this second level of the polynomial hierarchy. So we're actually dealing with harder problems than for example, MaxSAT. And then a bit also maybe about a domain-specific instantiation based on MaxSAT or SAT, but still in a specific application domain, which is a little bit about discovering causal relations from data. Okay, so the most commonly probably known for this audience is the MaxSAT IHS approach. So maybe I'm preaching to the choir, but MaxSAT is nowadays the worthy declarative optimization paradigm for NP-hard optimization problems, and we're essentially dealing with well, there's two ways of phrasing it. We're dealing essentially with linear cost functions, and our constraints are causal constraints, like so logical ORs over Boolean variables and their negations. And another view, a more classical view, would be that we have some set of hard clauses H and a set of weighted soft clauses S, and then we're trying to find a solution that an assignment that satisfies all the hard clauses and then minimizes the cost that's incurred by not satisfying soft clauses, and each unsatisfied soft clause will give us a cost according to its weight. Alrighty. So what's a core in MaxSAT? So on the MaxSAT level, we can think about like this. So we have hard clauses H, soft clauses S. So a core is a subset of the soft clauses, such that those soft clauses just viewed as clauses together with the hard clauses form an unsatisfiable Boolean formula. So the hard clauses are a background theory, but are not part of the course. They don't participate in the course. So essentially, for any core, we know that some clause in the core needs to be removed to make the remaining formula satisfiable. And that's essentially exactly what we're doing, using this so-called heading set duality. So we're trying to find a minimum cost hitting set over the set of coarse or minimal coarse crystals of this. And this is how sort of typically, especially when talking about MaxSAT and these declarative approaches, I like to sort of advertise IHS by saying that we're combining the main strengths of SAT and IP solvers. So we are using SAT solvers that are very good at proving unsatisfiability and providing explanations in terms of course without overhead. And we're using integer programming technology for the optimization of the hitting set. So for the hitting set computation. So for MaxSAT, it works like this. Then so again, so you have the notion of cost, so the cost function, so the weights of the soft clauses, you have the hard clauses and soft clauses here. The SAT solver in any sort of rudimentary implementation, at least just use this as clauses. And then we'll start with the empty hitting set and empty set of course, and then we're essentially asking, can we satisfy all the soft clauses together with the hard clauses? Typically you cannot if we're solving an actual optimization problem, so we can get a core from the SAT solver. And so then minimum hitting set problem gives us a hitting set, and now really you can phrase it like this. So a hitting set is now a set of soft clauses, and what we're doing in the next SAT solver call is where we're calling the solver and they're always on the hard clauses, but restricting the set of soft clauses considered by ruling out those that we used to hit in the latest hitting set, the current set, of course. And then we do this until we are the SAT solver says here's a solution actually, and then again, so this is then guaranteed to be an optimal solution to the MaxSAT instance. Great. All right. So for the remaining two, so let me continue with motivating a bit what's causal discovery and how it's important but hard problem to solve, and I'll mention a few words on how we instantiate IHS, right? This is pretty much to illustrate, sort of mention in words at least, that if you sort of have a problem in mind that you want to solve, the IHS approach allows you to actually sort of tweak a generic, say, IHS MaxSAT solver to solve the problem more efficiently by essentially tuning the techniques towards the problem I have. So what are we dealing with causal discovery? So we're given some data over random variables, and then we have a magical function here. Let's not talk about that, but we have a way of computing so-called independence constraints out of this data. So we have we do statistical tests on data, which gives us these types of independence constraints, saying that, for example, random variables x1 and x3 are independent when we don't condition on any variable, and then there can be conditionings of variables, and then we can also have dependence constraints like so that say that, well, look, these look to be dependent. But from the statistical test, we also get these confidences, essentially, or weights that state that how confident we are in these constraints. You can think about it like that, at least. And then the discovery task is that let's throw away the data and work on these constraints. And we want to essentially find a so-called causal graph structure that sort of represents as well as possible the underlying causal relations that can be inferred from these constraints.
So we should think of this as we're sampling, like every row on the left is like an assignment to x1, x2,
oh,
x3.
Yeah. It's just observations.
Okay, and based on these observations, you somehow decide that you're pretty sure, I guess, that
this is sort of a representation of the data in terms of this.
Yeah, which says that x1 and x3 really look independent to you. but the x2 and x3 are somehow highly correlated or anti-correlated.
So the problem is that these things, these constraints, can't be assumed to sort of be non-conflicting.
Mhm.
And now we have an actual optimization problem, sort of trying to see like what is the sort of causal presentation that optimally sort of satisfies this set of constraints.
And the causal graph, we should think of it as like the arrows are implications, basically.
No.
It's more complicated.
It's a bit more complicated. So there can be cycles, and there can also be bidirected edges, which actually represent latent variables. For example. So the thing is that, as I wrote here, so the task is that we're given all these weighted conditional independence constraints, and we want to sort of find a graph that sort of minimizes the sort of cumulative cost of not satisfying some of these independence constraints. So this is sort of the objective function, but then there's this horrendous constraint when we talk about this very generic model class where we have these can have these cycles and we have covering latent variables. So we have sort of two types of arrows, two edge relations, and we can have cycles. And in this class of models, the notion of deseparation, which sort of characterizes independence. So there's this sort of the satisfiability of these independence constraints maps to this sort of deseparation condition. And this condition in this set of graphs is quite a horrendous thing. So you can go and look at our group's web page. So on the main header page, there's a photo that I took out of the logical representation of this condition, and it's pretty fun. Right. Oh yeah, but there are sort of underlying logical constraints that tell us. So it's a very complex form of reachability that we need to decide.
So we should think of this as writing down the specification of the problem will be huge, and therefore we'd rather probe it and learn things about it. And that's somehow one application where implicitly thinks that shines, where
I don't know. So my main message will be here that if you look at this problem, for example, you can do things differently. And actually a MaxSAT, pure MaxSAT, sort of an IHS MaxSAT solver will fail because, for example, the SAT solver does the core analysis gives us horrendously sized cores if you just give the SAT encoding of this deseparation condition. But there are cores of size 3. And you can actually form these so-called core templates that then give us these small cores, and you can instantiate it based on the input that you get, the instance that you get before you actually compute any cores with the SAT solver. And this is one way of speeding up search horrendously. Okay, I should speed it up. But the idea really is that now we're working on these independence constraints, and we are computing cores over them. They can be huge. And it's hard to compute these cores, it turns out, and then once we hit sort of optimally, implicitly all the cores, then we obtain an optimal causal graph. So as I said, so what we're actually doing in an HPI paper that presents is not this one, but it's based on the encoding that was presented here. Essentially, we have these weighted soft constraints that are these independence constraints, so they're just sort of unit soft clauses in MaxSAT, and then we are searching over this search space of causal graphs that's sort of formulated as these deseparation conditions for each of these independence constraints. Logically, so as a Boolean formula, which is quite complicated. But if you think about it, this is just the sort of the MaxSAT IHS loop phrased in terms of causal discovery. So now what we're giving it is this the deseparation, independence constraints, and then the formulation of the deseparation condition, and then the weights of the independence constraints go there, and then we just do the same loop, and it's essentially just running an IHS MaxSAT solver on this problem. However, so let me just talk a bit about this slide. So So what we noticed is we started sort of just using IHS, MaxSAT IHS or MaxHS to sort of try to solve this causal discovery problem. And then we said that why doesn't this work at all? This should work much better. And then you go about and look at what's going on. And the first thing you noticed is that the SAT solver was giving us cores that had more than 50 constraints in them. And if you have to work on Finite set problems that have 50 to 100 constraints, course with 50 to 100 independence constraints or elements, this turns out to be quickly infeasible to really solve things fast in practice. And in particular, this was really problematic because then when you go and look at these problems, you realize that there's really, like, I didn't write them up here, but we have a sort of a core templates of 7 types of different cores that you can actually, if you give sort of input to this problem, you can instantiate the templates and gives rise to cores that are of size 2, 3, and 4. And of course, if you look at this loop, if you know your problem and you know how to derive cores, you just plug them here, right? You don't call a SAT solver first. You want to sort of feed as much cores here as you can. Well, you don't want to suffocate the IP solver, but especially sort of these, when it's very hard for this guy to find these sort of minimal cores, you want to feed information on it to guide this search forward. And this turned out to work really, really well. Then, because the encoding is very large for the deseparation condition, what we ended up doing is the sort of a dynamic partial encoding of saying that we are sort of essentially in the SAT solver turning off parts of the encoding in order to sort of focus the SAT solver search on the relevant parts. And then another thing is we haven't talked about how actually the core extraction works in a SAT solver, but in MaxSAT IHS solvers, what's done is essentially you ask for a core, and then it turns out to be very important to minimize the cores. And what's done is with some time resource constraint, you're doing sort of asking naively that, okay, can I remove this element from the core? Can I remove this element from the core? Can I remove this element from the core until you actually have minimized the core? But because the SAT solver in this domain, for example, is giving so huge cores, this turned out to be really bad. But on the other hand, the thing is that there's so few, the instances were so small that we could actually do something, a completely different core extraction technique that people really haven't tried, I don't think, anywhere else in IHS, where we started sort of, we don't do a destructive core minimization, but rather a constructive one where we started sort of cumulatively adding constraints and checking whether we already reached unsatisfiability or not. And this turned out to be much more effective. And so forth. Okay. Maybe this is the last thing. So just because I want to mention that maybe people haven't thought about this that much, but IHS you can instantiate for as hard optimization problems as you want, pretty much. Say on the higher levels of the polynomial hierarchy. Again, these illustrations are by Paul, so quite neat. This is to motivate propositional abduction. So very modern motivation. So let's say you're dealing with, nowadays I guess we deal with some sort of deep neural networks. And so we have some sort of a classifier. We get a photo and then it says cat. Yeah, this is a cat. Right. So you can think about it as, so we have these pixels, and so they're a set of hypotheses, and then we have a theory that's the classifier, and we are observing stuff output by the classifier. It says a cat, and now we actually want to sort of be able to explain why the theory supports the observations. And in this case, sort of the observation is correct. But sometimes, as we, I guess, know, the theory can sort of hypotheses sort of lead to the theory producing a false observation. And now we would want to explain based on the observations and the theory, why is it that sort of find a very small sort of explanation of the set of hypotheses, from the set of hypotheses, why the theory led to this observation that this guy is a bicycle. And in this sort of illustrative example, it might be some small subset of pixels that you know that actually then gives us an explanation why this network in question doesn't really work well. Right? So more formally, there's a problem called propositional abduction. It's part for the second level of the polynomial hierarchy, and it's essentially talking about, again, so we have some underlying background theory P, and then we have a set of manifestations or observations M, and then we are to explain the observations under the theory with a subset of a set of hypotheses that we're getting. So what do we require from a solution? So a subset of a set of hypotheses to be a solution to this problem. Well, we require that it's consistent with the theory. Okay. And then we require that it sort of explains the manifestations or observations. So you can think about these, the pixels that led this theory, the neural network to claim that it's a bicycle. Yeah, and then there's people have in the literature considered sort of weighted propositional abduction, so you can have costs from the hypothesis. Okay. This is such a fancy looking illustration that I want to end with this. Okay, so again, so you see there's an implicit that's over, and then there's some sort of a core extractor. This looks a bit too complicated than it needs to be, as was shown later on by others. But let's go with this because this is hopefully somewhat easy to still explain. So again, so we have some costs for selecting hypotheses to explain the observations with. And then the observations or the manifestations and the theory goes to the core extractor. Here's something interesting happens though. So if you look at what we were to be checking is the entailment of the manifestations by the theory and the set of hypotheses, right? Okay, so we need to do an entailment check. So and this is of course done. So it's a cohort problem. So we're doing a counterexample query to the SAT solver. So this ups SP just means the theory and the potential candidate solution. Okay, and the candidate solution will always be a heading set of our course. But what are the cores in this case? So we asked for a counterexample. So it means that if this formula here, so this is the counterexample for the entailment of the manifestations from the solution candidate and theory. So we're saying that, you know, solution candidate and theory and not some manifestations. So not all manifestations are covered. Is there a solution to this formula, which would be a counterexample for the entailment? So if we get a satisfying assignment from the SAT solver, then we get a core, right? So now it's not that we proved unsat and got a core. We actually get a core from the counterexample. What the core is essentially saying that look, the counterexample satisfying assignment in the assignment there's some hypotheses that are not used, and those are the ones that are assigned to false. To 0 by the assignment, And you need to hit at least one of these guys, because you didn't entail all the manifestations. So what this means is that we need to restrict this theory further in order to entail the manifestations. Okay. And if this is unsatisfiable, we still need to check that our candidate solution is consistent with the theory. One could sort of save iterations here, but in this case, let's do it like that. So then we still need to check if this guy is satisfiable. So it might turn out that our candidate solution is still not consistent with the theory, and that led to this MaxSAT result. And that, if that's the case, then we obtain another form of a core, which in this case is a bit trivial, which is just saying that, look, again, you need to hit something outside the candidate to cover the manifestation. Oh, to be consistent with the theory, sorry. So in each case, we get a core. In one case from the MaxSAT call, the MaxSAT result, and the other from the SAT. And then we do this until we get a solution. And that's bound to be an optimal solution to the problem. All right.
So 2 questions if you go back. So the first core is basically just telling you that you need to include like one more feature. Those cores are in general like going to be huge, or like the first type of, when you get a SAT call, it just says you have to include, out of everything you omitted, which is hopefully most things, you have to include something.
Yeah, we actually did something more clever here, which I remember what it was.
Okay, so you do something slightly smarter.
Yeah, we do slightly smarter, so we don't add an at least one constraint actually to like this solver, but an at most k, and that works much better.
Okay. And how would it be that ABDPS is, like for your example, that being unsatisfiable would basically, how could that happen? You say this is not a picture. I mean, or like how would the theory and the input be inconsistent in the picture case?
In the picture case, no. But in the general propositional abduction problem,
it could happen.
Yes.
Then it's like some input is badly formed or something.
Yeah, you can think about it like that. Yes.
Okay.
So you have to be consistent with the theory.
Okay.
Okay. So now, how to make IHS work in practice? This is just some random thoughts that I came up with. One is that I didn't mention that actually the termination is based on bounds information in all of these implementations. So you actually don't always compute the minimum cost heading set and then just check satisfiability with a core extractor. Rather, you terminate when the upper and lower bounds meet, and you we embed a lot of different techniques that give us both upper and lower bounds. And this is sort of an ongoing process of discovering more ways of improving bounds faster, or coming up with combining different techniques that together reach this termination criteria as fast as possible. We try to harness a lot of the potential of both the core extraction side and the minimum cost heading set side. So and the neat thing here is really that you can use both techniques from IP solving, like reduced cost, for example, and then different types of improvements to core extraction strategies. And then if you really want to solve a particular problem, this approach sort of allows you to fairly easily get into the solver and improve it by, for example, feeding it sort of known cores by using core templates, as well as sort of coming up with, say, problem-specific core extraction strategy. But yeah, this is all I had to say. Unfortunately, I'm a bit over time already, but yes, this was the implicit heading set approach. Hopefully, this was something new for everyone. But yeah, the typically you go about taking decisions over like SAT solvers that can provide us scores, and then you use state-of-the-art integer programming solvers for the insight computation. And this is really a main MaxSAT solving paradigm today among the others. But this really, I wanted to point out that this generalizes to harder problems, and you can instantiate it for whatever types of problems really you have in mind. The practical efficiency depends on how you sort of what's available for you as a core extractor. We've actually have a recent paper also on computing smallest MUSs for quantified Boolean formulas, and this already allows us to solve some sort of application-oriented instances in the realm of computational argumentation, even though sort of there's definitely ways of further improving core extraction efficiency in QBF solvers. All right, thanks.
Yeah. Questions? So one question from me is, so if we focus on MaxSAT implicit things, that there are some extra bells and whistles like abstract cores, for instance. Would you, like, suppose I wanted to do, I don't know, propositional abduction maybe, or something like, is there like a way to say, okay, I heard these MaxSAT people are doing fancy stuff, I want to incorporate this in my other IHS solver for this other domain? Did you like do the techniques transfer?
Yes. Yes. Yes, that's the fancy thing, really. That you know, these are sort of almost everything is sort of usable in any context, I would claim, and then it's just about finding the right balancing, because it's really like it's not like everything, all the other like ways of combining different techniques together that work for MaxSAT would work in other settings. And it's more like if you take everything that's been done for MaxSAT, the question is, can you do more? That's maybe more.
I would not expect abstract cores to work well in the exact same way as they're used in MaxSAT.
Yeah.
But I can make you up a way of adding them.
Yes.
And then you have to tune them to maybe make them work.
Okay.
What does implicit mean in the name?
Implicit hitting all cores, I assume.
Yes.
I didn't come up with it. We are very explicitly hitting, right?
Yeah, but I think the problem is implicit, right?
You have to hitting all cores.
You have a hitting set instance, but nobody's telling you. You're just saying, here's your universe of elements.
But
So if you compare to core-guided MaxSAT, then we're very explicit about the course.
But you don't explicitly know all of it.
Yes,
Yeah.
exactly. That's what I meant.
So you're hitting in the dark, and then every time you miss, someone says, haha, here's something that you weren't aware of.
You just ask another guy who's just like, no. Here's why. Here's one, and so that's the nasty thing. Right? The other guy says that no, and here's, by the way, one reason why. I could tell you more, but
So it's more it's sort of interesting also because so one way of thinking about it is like you have a hidden instance that is revealed to you like one set at a time, but then as you mentioned, like actually the quality of this oracle, you can affect it, like it could give you like bad sets, right? I mean, the smaller the set you get, it said no, you have to satisfy one of these three things. But maybe it will instead, if the core extractor is crappy, it says no, one of these 10 things have to be true. Yes. When in fact a better core extractor would have thrown away 7 of those 10 things and said no, you should focus on one of these.
So it can happen that I'm pretty sure that there's also one could find evidence of say MaxSAT domains where actually MaxSAT, like my IHS MaxSAT is solvers are not doing well just because the SAT solver just can't find the good cores. You know, it can be a sort of a needle in a haystack problem, especially in the causal discovery. That's just one example where there's just a key. like these really small cores, but the search space is so huge that the SAT solver just tended to give us sort of cores that are just ridiculous. And then you can't, because they are just so huge, you can't go about really minimizing them, because it would take too much time.
Other questions or comments? Otherwise, I think we're thanking Matti again. You want to give a break or? And now we're taking a break. So we're back after the break. Jeremias Berg is taking over. Will tell us about implicit hitting sets for pseudo-Boolean optimization. Please, Jeremias.
Thank you very much, and thanks for sticking around. Here I want to mention, except for Matti, of course, also Pavel Smirnov, who was a student of Matti's and who finished his thesis in early this year, February, something like this. He did quite a lot of work on actual implementation of this solver. So what's the goal of this part of the talk? I want to describe a fairly recent open source IHS-based solver for the pseudo-Boolean optimization problem. And to create somewhat different to what for example, Matti was talking to in introduction, I want to go into this idea of what is a core in pseudo-Boolean solving, and does it actually pay off to do these general kind of things that Matti was saying. And also mention how we go beyond a pure IHS-based algorithm and also incorporate what we call solution improving search, and show that that also pays off and allows us to simply solve more instances. And then I'll overview a number of these other techniques that are used in order to make this work in practice, and hopefully answer all of your questions about the techniques that I don't cover in that much detail. And then I also have some nice graphs for you showing how this performs compared to other approaches to the Boolean optimization, how this compared to CPlex, a sort of commercial IP solver, back to all of these nice techniques that we actually have on the performance. And as I said, at any point, if you have any questions, feel free to ask. All right, so what is pseudo-Boolean optimization? I'm assuming most of you know. We're dealing with 0-1 linear constraints with integer coefficients and binary variables. An example, I said I would be mostly going by examples. So we have a linear objective function that we want to minimize, and then we have a number of constraints that we want to adhere to. So I will be using terms like objective, I'm denoting that with an O, the whole function. Objective variable is something that appears in the objective, and then the rest are constraints. And I'm a MaxSAT person, so I'll be using F for a formula. And why do we want to do this? Well, pseudo-Boolean optimization is a central fragment of integer programming, and it provides a sort of natural generalization of projective normal fault causal constraints, and and you can pretty easily show that the theoretical power, reasoning power, when you have pseudo-Boolean solvers from pseudo-Boolean languages goes beyond that of CBCL-SAT resolution. So how have people tried solving pseudo-Boolean optimization in the past? Well, perhaps the most classical approach is to take an IP solver and throw it at it. So there are a number of very well optimized integer programming systems, Skip, CPlex, Groby, pick your favorite one, and they use variants of this branch and cut algorithm with a number of pre-processing techniques and probing and all kinds of fancy things. But more recently, and perhaps for us more excitingly, there's also been work in extending this conflict-driven paradigm from SAT to pseudo-Boolean solving, and also algorithms from MaxSAT to the Boolean solving. This is work done in this group by Jakob and his collaborators. And this is something that we very much make use of in our work. So thanks to you. All right, so this picture you've seen a number of times now. As with most other instantiations of IHS, we have here as well an oracle that gives us cores. For us, this is very much for running that. And an IP solver that computes hitting sets. And sort of on the first steps of breaking stuff that Matti was talking to you, I will say here that instead of just getting this one core, we will actually always get a set of cores and a solution to our problem. So at every step when we're here, we are also getting one solution that gives us an upper bound because it's a solution. And then when we go to the other side and we look at our course and we compute a heading set, it's fairly easy to, if you just think about it for a bit, the cores are something that need to be satisfied by all of the solutions. So if we have any subset of the cores and we know what the optimal way of hitting those are, then no solution will ever be able to achieve a cost that's better than that. So the heading set actually gives us a lower bound on the optimal cost of the full instance. So this is sort of what Matti was saying when he said that termination is very much based on these bounds. So we don't terminate immediately when we get set. We terminate when we find an upper bound, a solution that has an upper bound that matches a known core. So then, what is a core when we talk about pseudo-Boolean optimization? And a very natural first idea that we also used is what we call a causal core. So it's a subset of the objective function variables such that not all of them can be assigned to 0. So something has to incur cost. Here in the example, it's fairly easy to see that we cannot put both x1 and x2 to 0, because then we have to put a1 to 0, a2 to 0, and then we'll get a conflict. These examples are very naive. I'm suspecting rounding set could figure this out much faster, but if this bothers you, you can think of these as any set of constraints that entail one. So the causal core is then a subset of these objective variables, which is equivalent to then this at least one constraint. We have to set at least one to true. And these are computed by an extension to rounding set, which is taken from MiniSat, which in practice performs sort of causal resolution after the search and gets this subset or this clause. So it's a more lightweight procedure than the pseudo-Boolean conflict analysis that's actually being done. But on the flip side, we only get costs. A heading set is then either a subset of all subset of objective variables that hit all of the cores, but for this presentation, it might be better to think of it as a solution to these core constraints. The minimum cost solution to all of the cores that you have. And as said, this gives you a lower bound. And now we'll go through an example, and I'll go through this twice in order to later make a point of why general cores might not always fail. So here we have one large constraint saying I have to pick at least 3 of my objective function. And then I have pairwise constraints saying I cannot actually pick any 2 together or not incur cost on. When I say pick, not incur cost on. So here the optimal cost will be 4. We can only leave out 1 because of these guys. And what would then an IHS algorithm with causal cores do? In the beginning, we have no cores. So the heading set is simple to compute. We just assign everything to 0. We're saying we don't want to incur cost on anything. Now we go to routing set and ask it, is this a solution? And routing set will say no. But instead of just giving us one explanation, we can actually tell it to give us 2. So here's one explanation for why this heading set is not good. We have to put either x1 or x2 to 1. But then we can continue. We will, in practice, what we do is we remove these from consideration and ask how about the rest? Is the remaining part okay? And rounding set will again go no, because you also need to put either x3 or x4 to false. All right, so we're not done. We'll go back to the IP solver. And the last step we can also get. After that, we will remove one more, and the rounding set could give us, for example, this solution, which will give us the upper bound. And now we go back to computing the heading set. Now we have these cores. So a possible heading set is something like this. We have to put 1 from each core to true. And I said this is a lower bound. This has cost 2, so we know that the lower bound is 2. We go back to rounding set. And now we're asking, is this okay? Is this a solution? And we'll get more cores. No, you will also have to put either x2 or x3 to true.
And do we want to know at this point if you're giving the full assignment or if you're just giving the false variables?
In pseudo-Boolean solving, we would be giving the full assignment. It doesn't all change the point of the example, but yes, we would here be giving the full assignment.
Okay.
In MaxSAT, we would be giving the false literals, and this is based on experimental evaluation. Theoretically, you can do both.
Yeah.
So the intuition is that we want to enforce what we don't want to. We have to force it to not incur cost on something. We don't have to force it to incur cost on something. The course sort of automatically say, well, I have to sort of incur cost on this. But in experimental evaluation with rounding stat, it turned out that it's better to give it a hint saying, well, actually, here's the guys you have to.
Which probably means that rounding stat is crappy at search because it should figure this out, but it doesn't.
Yeah, because implicitly, if we leave out the true literals, those are the only ones it can hit. So it should be fairly easy to say, well, okay, I have to put this.
Yeah.
But it turns out that
It'd be interesting to understand why.
And then a loop like this keeps on going. Notice how when we go back to compute the hitting set, there's no reason to add a third literal here. We can instead just hit both of the two last cores on each. So we don't get an improvement in the lower bound. But, and in the end, when we've done this enough times, we've extracted all of these cores, and now we'll get a hitting set that sets 4. And again, I repeat, the hitting set here is not the same. We got the optimal solution early, and they don't have to match. So we terminate because the bounds match. We can terminate immediately after the hitting set. We don't have to go ask it for a solution that matches the hitting set. We'll get back to this example after discussing a more general type of core. So we're doing the hitting set computation with an IP solver. There's no actual reason to have to restrict it to at most one constraint. Same example as before. We saw that this x1 plus x2 greater than 1 is a core, but actually it turns out that it's not enough to put just one of them through. You have to put 2. So there's another core is x1 plus x2 is greater than or equal to 2. This is what we call a pseudo-Boolean, a PB core. And this is then any linear constraints over the objective variables that is implied by the constraints. So that is satisfied by any feasible solution to the constraints that we have. And this is then here we're making use of the work by Jakob and his group on this OLL implementation where they extended the pseudo-Boolean conflict analysis to also give us this course, more general course. And the nice thing about viewing a hitting set as a solution to core constraints is that nothing changes. A hitting set is still the minimum cost solution to all of these kinds of linear constraints. They don't have to be at most ones.
No, they're not hitting sets anymore.
Well, yes, we're calling them hitting sets because of sort of historical reasons, but actually they're sort of, we've decided that these constraints are interesting enough, so we're going to focus part of the search on these, and then we're going to query an oracle asking, well, now we have a solution for these. Is this a good solution or not?
All right, I mean, of course, you can sort of define a hitting set, generalized hitting. When is a general core hit?
Yeah, sure. We could make up our own term.
But yeah, I mean, it's a once you view it in this way, you could somehow, for some weird reason, you could view it as having your small problem and your big problem, and for whatever reason, you decide to solve your small problem to optimality, and then you say, oh, does this solution give me a solution to the big problem? Oh shoot, it doesn't. Why? I should have considered something else in my small problem.
Not even to optimality.
No, right, right. But
yeah, we're getting to that too. But yes.
Sure. Yes, good point.
Now we're back to the same example, and now we're using the fancy new code from rounding set that allows us to get more general cores. We'll start with this trivial hitting set, and now we'll say that rounding set actually figures out that this guy is also a core. So we have to pick at least 3. So now the first time we go back to the hitting set solver, it will have to satisfy that. So it will pick 3 at random. And the lower bound immediately jumps to 3. Nice, we're happy. But now if you think about it, what will happen? We still have to prove the lower bound of 3 is not right. We have to get it up to 4. And now since every single hitting set that we get needs to satisfy this, it will always set at least 3 of the variables to true, leaving only 2 that are set to false, which will hamper the disjoint phase. Because now when we go back to rounding SAT, it can only give us this core and nothing more. Well, previously we could always get 2 cores, and if you increase n a bit more, this difference will be even larger. And now we have to go back, and now we have to find 3 literals that also hit this. And now we go back to rounding SAT, and it will still not be happy with us, but it can only find us the 1 core. And now, even though we have this nice pseudo-Boolean core that allows us to bump the lower bound up to 3 immediately, we're actually not saving anything. We still have to find all of these other cores. And now we're doing it worse. And even though this example is a bit contrived, we actually observe behavior like this on a real world. Well, benchmarks, we'll get back to those later. So even though you can use pseudo-Boolean cores, it's very much an open question when you should and can you somehow find a middle ground between these extremes. But yes, once you're here, you'll again get the lower bound to be correct, and then you can determine it. So we still have to find exactly the same cores. Now we just spent 1 extra step finding an initial really nice lower bounding core that then actually hurt us. In some ways, hurt us more than helped us.
I mean, one thing is that you could always find the core, right? And you could add it, and then you could say, if you really believe in this, I guess this is weighted core extract, or what's the this independent core? I mean, you could always weaken it to the smallest clause you can, and then keep going, right? But keep the strong. But yeah, maybe no, that doesn't help because you're worried about the hitting set computation. Okay, sorry.
Yeah, we want to find more cores than 1, preferably, because computing a hitting set is hard.
Yeah.
We want to avoid doing that.
Yes, sorry. Yes.
Yeah, I mean, and I could make up other examples where pseudo-Boolean cores allow you to terminate immediately. I could increase that to 4, and then we're done with it.
Yeah, no, yes.
So I mean, it's not very much not clear. It depends.
Yes. Yeah.
It just depends on whether it's 3 or 4.
If 4, from that. All right, I'm going quite fast, but stop me if you have any questions. As Matti also said, we do a whole bunch of different techniques on top of the pure algorithm. The blue ones are the ones I'm going to be spending a bit more time on. And then I have slides, or I've ripped off Matti's slides for the other ones that I have at the end. So if you want to hear about them, we'll see what the time is at that point. And the goals of these techniques are very much to sort of get better cores, although I just told you we don't really know what a better core is, but somehow some kind of intuition. Get good bounds, preferably without stopping termination. And also fix variables. That seems to be always, if you can fix something, that's nice. That makes it more easy. So solution improving search, and I noticed while Matti was talking that there's an error on this slide, but it's a complete algorithm in itself, and it's sort of an upper bounding approach, where you have your constraints and your objective, and you add an extra constraint that's supposed to be slightly weaker than that, but not much less than or equal to upper bound -1. And now, essentially, we're asking the oracle, is there a solution that's better than the one that we already have? And then we keep going until the oracle says no. Rounding SAT has this implemented in itself, so you can use it as an optimizer. And in IHS, in our solver, we do this heuristically. We don't have to sort of invoke it all the time. Instead, we look at the bounds that we have And whenever the bounds are sort of stagnating, so nothing is happening, then we say, well, maybe we should try something else. And then we go invoke this solution improving search for a while, for 30 seconds under default limit, and then we come back. And there's this nice interplay between these algorithms. It might be that the solution improving search gives you a solution whose cost matches a lower bound that we got from IHS, and then we can terminate without having to do the sort of unsat last call of solution improving search, which is nice. Constraint seeding is another one of these really important techniques. If you accept cores as constraints over the objective variables that are entailed by the formula, then constraint seeding is a very natural idea. We've seen examples of cores that are part of the formula and those that aren't. So if they're a part of the formula, we'll just scan them and then we add them to the IP instead. Well, I think we also add them to running set, but we add them to the IP as well before doing anything. So essentially, we're getting cores without having to do search with running set.
Would this ever be bad? Or do you always do it?
Well, I mean, if we have a scheme where we add this one, but not those ones, then we already seen that it could be bad. But in practical implementations, I'll have a plot showing that it's one of the most important techniques we do, and I cannot sort of think of an example where it would be bad.
Mm-hmm.
But maybe, I said, we don't really know what cores are good. So then what was sort of hinted at already, it turns out we don't even have to compute the hitting set optimality every time. If we have an optimal hitting set, we can get lower bounds. But we can also, what we actually do is we can terminate the IP solver as soon as the candidate hitting set has cost lower than the upper bound that we already have. And why is this good? Well, it's faster. But the fact that we can get cores from a hitting set is not dependent on it being optimal. We can get cores from non-optimal hitting sets, and these cores have to be satisfied by the every solution anyway. So they're, in the sense, we can just use them. You don't have to have an optimal hitting set to get cores. And if we don't get a core, then the first solution that we get will have cost exactly equal to the hitting set that we used. And since we stop it only after it's better than the upper bound, then the solution that we get is guaranteed to improve the upper bound. So either we get new cores or we improve the upper bound. And I think in the current implementation, we have a heuristic that per default computes these non-optimal hitting sets. But if there's ever a case where we don't find cores with a non-optimal hitting set, the next hitting set is forced to optimality. And this is, again, we've tried and it works. And the intuition is very much that in the beginning, when we don't have that many cores, we don't expect an optimal hitting set to actually lead to any kind of termination anyway. So we'll just stop early and get some more cores. And then we'll care about optimality a bit later. So maybe what's time? I'm going really fast, I think.
In 3:45.
So we'll look at some plots, and then if you're interested in these additional techniques, we can talk about them then. So we're using rounding set, the so-called learn to relax implementation that uses fancy LP techniques as the core structure. Cplex as the hitting set solver. If you want to try the solver, you can find it there from Bitbucket. And as benchmarks, we collected sort of 8,000 or almost 9,000 benchmarks from about 60 domains and did a balanced sampling from these, taking max 30 per domain. So we ended up with around 900 benchmarks in the sample set. And as default parameters for the solution improving search, we run it for at most 30 seconds whenever we invoke it. And we trigger it whenever the lower bound has not improved for about 5 iterations. Here's the sort of results on the sample set using different cores and the additional solution improving search. So the red line on this plot, you want to be as high up as possible because you have the benchmark on the y-axis and different timeouts on the x-axis. The red line is the rounding set implementation doing solution improving search on its own, the one we actually use as the core extractor. And what we can see here is that what seems to pay off is the addition of solution improving search. That seems to have a larger effect than the kind of course that we use. If you look at the three lines over here, black one uses this more general pseudo-Boolean course, and then the dark green one, which is very hard to even see a difference on, uses only causal course. But the jump happens when you add this solution improving search. This is what you get if you don't use solution improving search. And now, why do we sample? Because if we do the same plot over all of the 8,000 benchmarks, it looks like this. So now rounding set is doing really good.
But that's not the reason.
That is not the reason. Rounding set and the version of our solver that uses solution improving search is doing really good. And the keyword here is we want to be doing solution improving search, which I'll show you on the next one. And the rest of them are doing. There's not too much interesting to say about the rest of them. But so what's going on here? It's the fact that these benchmark domains are hilariously unbalanced. We have about 61 benchmark domains, and about 40 of them only have most 50 benchmarks in themselves. And of these 8,000 benchmarks, over half of them come from 4 domains. So let's look at those domains, and especially the BA domain, which is the one domain that exhibited exactly the kind of behavior I showed you in the example. Here we can see if we do IHS search without solution improving search, we solve 20 or up to 78. And as soon as we add solution improving search, we jump to 400 and over 100 for this. So this is the reason for the massive change in behavior. So if you were solving these benchmarks, you obviously want to use rounding set and then solution improving search. But in this benchmark set, it wouldn't be fair to sort of use all 8,000 because then you're actually only comparing the behavior on this.
More exactly, you cannot represent the results in such a plot if you don't balance the set. That's the point. Of course, you can make a table, but you can make such a plot that sort of puts everything into one plot.
So then you could also ask, how robust is this sampling? So what happens if I just choose a different random seed or something? In this plot, we took 10 different seeds for the sampling, and then for these 3 solvers, we plotted 3 lines. The min line for each solver represents the number of benchmarks solved in all 10 samplings. So it's sort of the worst case type of behavior. The max line represents the number of benchmarks solved in at least one sampling. So the best case behavior, and then the median is how many did we solve in at least 5 of the 10 samplings. So it's a sort of confidence interval type thing here. And we can see that that the relative behavior performance of these solvers seems fairly robust to this sampling. So then another question we often got asked, especially by MIP people, is that aren't you just using a MIP solver and aren't you just solving the pseudo-Boolean instances of MIP? So to sort of say no, we did this plot. And here we took the about 900 instances that were solvable and looked at how big of a fraction of the running time is spent in these 3 core parts of the algorithm, either extracting cores, computing the heading set, or so using the IP solver, or doing solution improving search. And we can see that very nicely that there is, we are actually achieving a sort of hybrid type performance where we're able to spend time in different parts depending on the benchmark. And not all benchmarks are solved by solution improving search, nor are all solved by pure IP solvers, nor by pure running set. So it's a very nice sort of combination of the 3.
But when you spend time on solution improving search, I mean, again, you said only regardless of even if solution is improving search is doing great, you're still switching it off after 30 seconds.
Yes.
So the only way that you get that much is like it's time and time again, it's trying to extract cores and improve the lower bound, and like time and time again, it just fails, and it's okay, let's go back to.
Or alternatively, if it solves it in 30 seconds.
Oh, you're saying this is not
This is a fraction of the
normalized.
This is
So I don't know, like, okay.
this is a fraction given an instance with how much time spent solving the instance.
Okay, if I would ask for the same plot for instances that take above 1,000 seconds, then you don't
might
know.
be, it might be different. It's probably
Okay.
not, yes. So that's good.
Mm. Because that would be, I think, interesting, like, you know, like easy instances say below, I don't know, 200, 300 seconds and above 1,000 seconds. Like, do I have the same picture, or is it?
That's a good point.
No, how it will evolve, who knows?
No, we didn't think of that one.
But if you think of easy instances, that will probably give more varied performance, like it's really some part that solves it.
But it's natural somehow. It's interesting. Again, these instances where you almost only do solution improving search. Is that because you do like search once and then you just nail it?
Yeah,
and it was easy,
so
right?
either it's
Or is it
that
like
solution improving search is the one that solves them fast, or that it's sort of those are the ones that sort of stagnate and are the hardest instances. But I think that based on what you had the table on the big benchmark domains, I would claim that probably there in some you need the solution improving search, and likely part of that are sort of made easy. Some of those are made easy, right? I would guess so. So part of that blue stuff are those instances for sure. My guess.
Yeah, I would agree.
It doesn't answer your question.
No, but
But sort of.
yes,
Some
it's
sort of
a good point. But would have been a good thought. Then we also have some comparisons to other approaches. We're doing a bit better, but as we've also seen, it can depend really much on the type of instance we're following. But what do you want to do?
And we don't want to have skip on this plot.
Oh, that's a good point. Yeah, it's a bit above. Not anymore quite a lot.
But it would be better.
It's slightly better than the newer version. This is the old version, but
Okay.
overall it's doing sort of, if I remember correctly, right? No, we have the data for Cplex.
Yes, Cplex is coming up in the slide, but not in this one.
Yeah, exactly. That's the issue.
So these are the sort of additional techniques and what their sort of marginal contributions are. I'll lift out the ones that I talked about already. You can see, as I said, this is what happens if you don't do contract fitting. So you lose a lot of instances. Dark line here is what happens if you force the hitting set computation to optimality on every connection. Is there any else? This RC refers to reduced cost fixing, which is a standard technique in IT, where you sort of say, where you can say, I will never need to put this, will never need to flip this variable because then the cost will be too high. And then
by the way, this is also for the earlier version. Right? Is it? I think yeah, this is the CP paper.
Yes, this is the combination. Yeah. And then here with Jakob teased this notion of abstract chords. We did try it here, but the version sort of straight lifting from MaxSAT turned out to not work as well. And I think one could sort of spend time on that and make it work well.
Yeah, that's likely not well.
But sort of to illustrate the point that I can tell you how that could work, but actually making it work is all different.
What is no shuffle?
Shuffle refers to once you're done with your running set search, I will then take my assumptions and I will shuffle them in some other order and go again, hoping to get another core.
And that's helpful. So you can just trivially propagate new cores by
Because
reordering the assumptions.
at that point we know that these assumptions will lead to a conflict. Now the question is, but they can lead to many different conflicts
And they do, that's the nice thing.
And how do you choose?
Randomly.
randomly.
We
Well,
tried,
I-
we tried strategies, I think nothing paid off. It's just.
Yeah, we had a number of different fancy ideas.
No, but you run roundings that you got a core back over, x1 up to x10, assumed in this order. Say. Okay, now you can try a bunch of different random orderings. I guess.
No, not focused on that.
Core, but
All
all of
the
our
assumptions.
assumptions. So we had
We want
assumptions
diverse cores, right? So you permute all of the assumptions.
Regardless of the weight.
Yes. We tried also
We
to.
tried some
fancy
way.
stuff. No, nothing.
Let's randomly.
Okay. So you're saying like deterministically just do sort of stratification, I guess, is that the word? No.
Right.
I don't think it's
No.
more about sort of I had 100 assumptions. First
Yeah.
I put them in order. I got something. Then
Right.
now I will put
Assigning
them
them one
in the
by one.
opposite order and get something else. And now I will shuffle them in any way.
And you just do this for a while to get
Like 20 times or something, 10 times.
okay,
You
and then
keep
take
what-
all the cores.
Yeah,
Yes.
yeah. We also
also
tried
tried picking
selecting.
cores.
Yeah.
That didn't work
I
either.
don't know. Nothing that we thought that might work did work.
Yes. We had nice ideas of looking at the reduced costs of the core variables and picking the ones that. have
And then
highest
it's
and
just
then
like
they work.
take some of them. Take 10. That's good.
And then still the simplex comparison, the point I want to make here is that whether or not that IP solver works better depends again very much on your instance.
Which version is this? I think this is not the new.
Do we have a new one?
Yes.
Where are you hiding all of this from?
What?
Where are you hiding all of this from?
Probably in Slack. So after 3 months, they go away and then you have to pay for your plots. No, but I think this is not the new one because it looks worse than it should look. No.
Don't look. But if
Or
the
was
point,
there more
if the
on the
point
like
here is-
complementarity?
Yeah.
Sort of,
Exactly, but I think my claim is that nowadays we have similar things. But yeah, so simplex is a bit ahead if you just would plot. There's sort of a
if you do a
cumulative whatever runtime distribution thingy.
Yeah.
But yeah, it seems quite orthogonal.
All right, so in the last two CP conferences, we presented the first sort of pseudo-Boolean optimization, instantiation, IHS paradigm. Tried a bunch of different things on it and managed to get something that works fairly well. But of course, there's still a number of open questions that are facilitated by the larger parameter space of pseudo-Boolean solving. What kind of course do we want? When do we want to add them? How do we sort of in a meaningful way get the bonds to match without hurting ourselves? Do we have to throw whatever we can on it, or should we be a bit more picky? And then I have a bunch of citations. Thank you very much.
So, questions, comments? So what's your, I mean, what do you think that general pseudo-Boolean cores do pay off in the end or not?
I think that with some work, hopefully, for example, together with you, we could figure out a way to make them work. At the moment, in the current version, I would say that no.
Because like one question that you could ask is the counterexample you had that was killing rounding set, which, as you noted, it wouldn't actually happen, but you could change it an epsilon fraction, and then you could get something that probably gives the effect that you mentioned. You're sort of, I mean, what you've done is you've taken a pseudo-Boolean constraint and then you've dumped it to CNF in an evil way. And
But
this,
I'm not saying
the
it's killing
pseudo-Boolean
rounding
solver
set.
just doesn't understand it.
I'm not saying it's killing rounding set. I'm simply saying it's killing the IHS approach to optimization. So rounding set is very nicely giving us that far, but then it hurts the rest of the algorithm. So now the question is,
Yeah, but there was at least 4 constraint hiding there, which we would have detected with at most 1 pre-processing.
if I mean that behavior was observed on this BA instance. They are not, of course, that plain, but the BA instances exhibited this where the pseudo-Boolean constraint got the lower bound almost correct, but not quite. And then exactly because that the rest
It
of the
took forever.
algorithm just started hurting.
Yeah, this really was really something that just like
That's
what's
weird.
going on? And this,
Do you ever throw away chords? Like this chord is always satisfied, we don't need it anymore, let's just throw it away. Would that maybe
That
help
isn't-
in this?
That would be perhaps, I think Peter Flecky had us a similar question sometimes, and that is a sort of interesting way forward. In
So
chat,
but
no,
the
but
question
here maybe.
the question is how often does it happen that the solver doesn't work because of the heating set problem? Guess what? You have to be careful about not trying to, make something easier that's easy enough. Right?
No, but I mean, we could throw away the most 3 constraint.
Yeah. But like my point is that like if I would try to improve on this solver, I would try to improve on the efficiency of the core extractor. Like that's where if it can be improved, that would be probably the most benefit. And then the other thing is like choosing between, like, how could you know which types of cores do you want to extract, right? Like based on the instance. But I'm not sure how often here the like IP solvers getting killed. Really? Do we know?
Probably not that much, but
Yeah.
Did you ever try running like rounding set as your IP solver?
I'll try that.
No, because I mean conceptually we have the small
Yeah,
problem and the
yeah.
large problem. It's like, why are we using different solvers? Well, maybe
Yeah. This is, I never heard this question before.
Typically it's always,
Why aren't you using a MaxSAT solver for that?
no, I mean maybe, but I guess there's a reason why you're using an IP solver for the hitting set computation.
We sometimes tried it for something like MaxSAT or something, and then it doesn't.
Because also for MaxSAT you could use a MaxSAT
you
solver
could, yeah.
for the
It doesn't,
hitting set,
like,
but
you
it doesn't fly.
you can always look up in the comment. It's been 3 years since you last tried. Let's try again. And then
Okay.
So, but some people have done this though, like John and others who did the smallest MUS IHS thingy. They actually use the MaxSAT solver.
Okay. But no, but still the conclusion is for implicit hitting set in MaxSAT, like the reason to take an IP solver for the small problem or the hitting set problem is that somehow seems, what do I know, some structure, something that's simply like IP solvers are good. And
like
then
at some point the argument that I would like to say is that look, if you have very heterogeneous coefficients in your cost function, then you just give them the IP solver.
I mean, you could go crazy, right? You could use a local search solver for that, right? Because you sort of, the whole point is you expect this to be satisfied.
Do a branch and bound algorithm for hitting set. No, just kidding. Yeah, but it's true. You can throw anything at it, but yeah, one can try. And as I said, the hitting set problems are really weird. I don't know what are typical real world hitting set problems, but probably not like this. So,
any other questions, comments? Otherwise, I think we'll thank both Jeremias and Matti again.
What?